Assalamu alaikum students. In today's lecture you will learn about the molecular orbital theory diagrams of diatomic molecules including boron, nitrogen, oxygen and chlorine. Now here it is given the molecular orbital diagram of B2. Before it you should know or you should remember what we have done in the previous lectures, that the rules to fulfill the molecular orbital diagrams. These are the energy diagrams for the filling of the molecular orbitals formed in this theory. Now, in this theory, we consider that all the orbitals of two atoms, which are the same atoms, they will overlap to produce molecular orbitals. These molecular orbitals, the half of them are bonding and the half of them are anti-bonding. The bonding molecular orbitals, they are of low energy and they are placed down there, while the anti-bonding molecular orbitals, they are high in energy. They are placed above in the energy diagram. The bonding molecular orbitals are stable one orbitals, while the anti-bonding molecular orbitals are unstable ones. So, what the number of electrons which are present in the atomic orbitals of atoms, they are placed in these bonding and anti-bonding molecular orbitals according to the rules or the principles, that is Afabo principle or the Hund's rule and the Pauli's exclusion principle. They all will be followed, that the filling will occur according to the increase in the energy of the orbitals. Secondly, two electrons can be placed in each molecular orbital, whether it is bonding or anti-bonding, so they will be placed there with the opposite spins. And in the degenerate orbitals, they will be placed first, the one of each electron will be placed there and then the doubling will be done. Right now here it is given the molecular orbital diagram of B2. One thing more, we have also to calculate the bond order, which will tell that how many bonds are possible between the two atoms. Right now here the electronic configuration of boron is given. You can see each boron carry 5 electrons in it. So its configuration is 1s2, 2s2, 2p1. Look at the energy diagram which is given. It is arranged according to the increase in the energy, as this line shows. The arrow, up-headed arrow, it directs that energy increasing in the upward direction, so that we have only the orbitals overlap given for the valence shell orbitals, that is 2s and 2p. You can see in 2p, 2s orbital of each boron atom, there are present 2 electrons in each, and we have only 2 molecular orbitals to be fulfilled for this level. It is 2s, sigma 2s, that is the bonding molecular orbital, and sigma star, that is the anti-bonding molecular orbital. This is sigma and this is sigma star. Now here in total we have 4 electrons in it, so 2 will be placed in sigma 2s and the other 2 will be placed in sigma 2, the sigma star 2s, right? So the whole number of electrons which are present in 2s is fulfilled. Now comes to the next one level. It is the 2p1 for each of the boron atom. Here it is the energy profile or energy diagram for the p orbitals. You can see the diagram is different than that we observe for the beryllium or the other one at higher atoms. As I told you earlier, that energy of the orbitals, it vary in accordance to that whether these orbitals they can mix or they cannot mix. It depends upon the energy difference between the orbitals. So here it is given that the mixing of the 2s and 2p occurs here. So that's why the 2p orbitals become higher energy, so it moves upward as it is given. This is the 2p or 2px orbital, which is placed above that of the pi 2py and pi 2pz, which are degenerate orbitals and will be placed down there, right? So here These are the atomic orbitals of both the boron atoms. You can see each one is holding one electron in it. Now we have the lower energy orbitals, that is pi 2py and pi 2pz as degenerate orbitals. They are located first. Here they are. So these are two orbitals which are present at the same level. So I will follow, or we will follow, the Hund's rule. So the two electrons from each side will come to the different orbitals with the same spin. As the two degenerate orbitals are available, so they will be filled half first, right? So here there comes two electrons in the pi 2py and pi 2pz molecular orbital, so that we have two unpaired electrons still retained in B2 molecule. This retention of the two unpaired electrons makes the boron molecule paramagnetic in behavior. Right, now this is the configuration which can be written for this B2 molecule. You can see start from 1s, it is star sigma 1s2 complete. The higher energy is sigma star 1s2, then onward go on with the increase in energy of the orbitals. Sigma 2s2 is placed next, then sigma star 2s2, then we have pi 2px with 1 and pi 2pz with 1 only, right? We just have to give the configuration of the central one or the molecular orbitals up till they are being fulfilled. Then we have to calculate the bond order. The bond order found there is, just leave it as it is given. The bond order for each orbital will be taken separately, right? For 2s, it is 2 minus 2 upon 2 is equal to 0. So no bond formation takes place for 2s. But when we say for 2p, again find out the bond order. You will find there number of electrons in bonding molecular orbital minus number of electron in anti-bonding molecular orbitals divided by 2. So the bond order of B2 will be 2 minus 0 upon 2. That will come out as 1. So there is only one bond formation which will take place between boron to boron, and the presence of unpaired electrons makes it paramagnetic in behavior, right? This is all about the molecular orbital treatment of B2 molecule. Come to the next one. It is nitrogen molecule given. You can see the energy profile of B2 and that of N2 are quite similar, as the arrangement of orbital is same, because in nitrogen also there is the mixing of the two orbitals, that is of 2s and 2p takes place, so that 2px become higher in energy, right? Now what is the configuration of nitrogen molecule? It is 1s2, 2s2 and 2p3. It has how many electrons in total? 7, right? Its atomic number is 7. We have to draw only for the valence shell, right? So here the two diagrams are given. One is for the 2s and the other one is for 2p, right? You can see each nitrogen atom, when it is using its 2s, it is completely filled. So the first diagram will be similar to that of the B2 2s diagram. Here it is given the 2s of 1, it is the atomic orbital of the one nitrogen overlaps with the 2s of the second oxygen nitrogen orbital. These are the atomic orbitals to produce two molecular orbitals, which will give rise sigma to s bonding molecular orbital and sigma star to s anti-bonding molecular orbital. Here they are, this one and this one. Again we have total electrons in it 4. So place them as a pair in the two bonding molecular and anti-bonding orbitals, so that they will arrange themselves in energy increasing order. So 2 electrons in bonding and 2 electrons in anti-bonding will satisfy the arrangement, right? All the 4 electrons are accommodated. Now find out the bond order for this 2s. It will be 2 minus 2 upon 2, that is equal to 0. No bond formation will occur here, right? Now come to the next one, the higher one. These are the 2 p orbitals of one nitrogen and these are the 2 p orbitals of the second nitrogen atom. When they overlap, the regions produced are that pi 2py and pi 2pz as degenerate orbitals. They occupy the lower place as compared to that of the sigma 2px, which is higher in energy. As I told you, this is higher in energy due to the overlapping with that of the 2s orbital before it goes for bonding, right? Now here each p orbital is holding 1 electron. In total we have 6 electrons from both sides. Each is contributing 3, right? So the total number of electrons which we have to accommodate, they are 6. We will fill up the 2py and 2pz pi orbitals first, so that there will be accommodation of 4 electrons in it. As you can see here, it is given, right? And then out of 6, 4 are accommodated, 2 are left. They will occupy the 2px to form a sigma bond. Anti-bonding orbitals will remain empty as none of the electrons left to be fulfilled there, right? Now what will be the bond order for this nitrogen now? This one will be how many electrons in the bonding molecular orbital? That is 6 minus how many electrons in the anti-bonding molecular orbital? Here anti-bonding. None. 0 upon 2. It will give you 3. Means nitrogen to nitrogen there will be present 3 bonds. One of them is sigma bond and the other 2 are the pi bonds, right? Here its configuration is given. Again I have to start from the sigma 1s, which was completely filled. Higher energy is sigma star 1s, and then we have sigma 2s2, sigma star 2s2 in ascending order, and then we have pi 2px equivalent to pi 2pz. Both are filled, 2 in each, and then we have the higher one, that is sigma 2px with 2 electrons in it. So this is the complete configuration of nitrogen molecule. Now here it is given the molecular orbital diagram of oxygen molecule. Oxygen with atomic number 8. It has electronic configuration 1s2, 2s2 and 2p4. Here you can see the outer electronic configuration is 2s2 and 2p4. Here the diagram is given for these two orbitals, that is 2s and then 2p4 is treated for the formation of the molecular orbitals. Here the energy profile is given. You can see the 2s of one oxygen overlaps with the 2s of the second oxygen. Each of the orbital carry 2 electrons, and we have 2 electrons to be fulfilled, that is sigma 2s and sigma star 2s. Each will carry 2 electrons, so that all the 4 electrons are accommodated. Number of electrons is equal in bonding and anti-bonding molecular orbitals, so that the bond order for 2s of oxygen molecule will be 0, right? Now comes to that of the p diagram. In the p orbital, each oxygen atom carry 4 electrons in total, right? Here 2p of one atom of oxygen and 2p of the second atom of oxygen. Now here the overlapping of these atomic orbitals with 4 electrons on each side, they will be accommodated in the energy orbitals like this, that the sigma 2px will be filled first, this one with the 2 electrons in it. Remember, we have to accommodate 8 electrons, right? 2 p orbitals are half filled and the third one is completely filled, right? Now here we have the 2 degenerate orbitals at the higher level. These two each will carry 2 electrons in it, so the total count here is 6, which are accommodated of electrons. The remaining ones are 2. Now the next higher available orbitals are pi 2py and pi 2pz as degenerate orbitals. They will be filled now, right? As we have just 2 electrons and these are degenerate, so Hund's rule is followed. We will place 1 electron in each, means they will be half filled, and the upper one, that is sigma star 2px, will stay empty, right? Now here it is given the bond order. Now calculate it, what it will be. It will be, just leave it, this one will be the, how many electrons in total in the bonding molecular orbital? They are 6. And how many in anti-bonding? They are 2. Divided by 2 will give you 2. So oxygen to oxygen, there are present two bonds. One of them is sigma and the other one is pi bond. Right? So bond order is 2 for oxygen molecule. Now you can see also that its anti-bonding orbital carry 2 unpaired electrons. So it carry magnetic properties. Whenever it will be kept in the magnetic field, these electrons will be deflected in the magnetic field, right? They give response in the magnetic field. So that's why oxygen molecule is considered paramagnetic in nature, which is the fault of the VBT, which is not going to explain that why oxygen molecule is paramagnetic. Here it is clear that due to the presence of unpaired electrons in its anti-bonding molecular orbital, it shows paramagnetism, right? Now the configuration is given according to the increasing order of the energy orbitals. It's given as sigma 1s2 is filled first, then sigma star 2s, then sigma 2s2, sigma star 2s2, sigma 2px2, and then there will be filling of pi 2px, 2py2, pi 2pz2, and then there will be the anti-bonding molecular orbitals, that is pi star 2py1, pi star 2pz1. Now this is the configuration of the two atomic orbitals and about for the that of the oxygen molecule, right? Now comes to the next one. A very favorite question is given in your exercise, that find out which one of the following, namely O2, O2 minus 2 and O2 plus 2, which one of them is paramagnetic in nature. We have done one of them, that is O2, which we find that is paramagnetic in nature as it is deflected in the magnetic field. Now what about O2 minus 2 and O2 plus 2? What does it mean? O2 minus 2 means what? And O2 plus 2 means what? O2 minus 2 means oxygen molecule has gained 2 electrons. Minus 2 means gain of 2 electrons, and plus 2 means loss of 2 electrons, right? Now the number of electrons for each of the p orbital, when it has minus 2 configuration, it will be, you know very well, the oxygen atom holds the configuration, that is 8 electrons. So 1s2, 2s2, 2p4. Now for each oxygen, when it gains 1 electron, it carries minus 1. In total, when it becomes a molecule, it acquires minus 2. So each atom is getting 1 electron before it overlaps for the bonding, right? Uh, Here comes that minus 1 means 1 more electron with each atom. Now the number of electron becomes 9 to be accommodated. The 2s diagram will be same as we have done for the oxygen molecule, but carefully look at the diagram of the 2p. Before there, in oxygen, we have placed 2 unpaired electrons in 2p orbitals and a pair of electron in third p orbital. while here we have two paired electrons in two of the atomic orbitals of p level and only one electron in this one of the p orbital. So the total number we have to accommodate from two of the oxygen minus one atoms, not atoms, but then this time they will be ions. It will be 10. Right? Diagram is same, no change in it, just filling will give you or filling will tell you whether there will comes a bond formation or whether the substance will be paramagnetic or diamagnetic. Right? Here we have sigma 2px will be filled first in p orbitals according to the ascending order of energy. 2 electrons accommodated. Sigma 2py 2pz will be filled next as they are degenerate, so they can carry 2 electrons in each, so 4 more are accommodated. The leftover out of 10, 6 are accommodated and 4 are left. These 4 electrons will move to the anti-bonding molecular orbitals, that is pi star 2py pi star 2pz orbitals. As these two degenerate orbitals are available, so by placing one electron in each, still there are two to be accommodated, so pairing will be done. So 4 electrons will be accommodated here. None of the electrons is left now to be placed in sigma star 2px. Now here it comes. It will have the how many electrons in total? That is 10. Find out the bond order for this. What will be the bond order? Number of electrons in the bonding molecular orbital, that is 6, minus number of electrons in the anti-bonding molecular orbitals, that is 4, divided by 2 will give you how many? Tell me now. 6 minus 4 upon 2, 1 bond between oxygen to oxygen. Is it? Now here we have paired electrons in all the orbitals. So the substance will be considered diamagnetic as there will be no any attraction in magnetic field for O minus 2. Now do the same thing with O2 plus 2. As I told you earlier, O2 plus 2 means one electron from each oxygen atom is removed. So out of 8, they have now 7 electrons in each. Right? So we will do the same thing. We will draw the same energy diagram for the O2 minus 2, O2 plus 2. Here there is a little change in it, but there's a mistake actually in this P diagram. Draw one of the p orbital, that is 2px will be down there and the 2pz and 2py will be up there. Same diagram is given for these, right? So here will be, thus you can see here this diagram is just similar to that of the nitrogen diagram. 7 electrons are accommodated in such a way that 2s bond order is 0, as the 4 electrons accommodating both the bonding and anti-bonding molecular orbitals, and then we have the filling in the p orbitals each type from each side of the oxygen plus 1 ion. Each one is having one less electron, so 3 are placed as they are degenerate orbitals, so 3 are placed in 3 different orbitals of p structure. Now the filling will be done in such a way that this is 2px will be filled first with the 2 electrons in it. Pi 2pz and pi 2py will be filled next. As the total 6 electrons are present, so place 2 electrons in each of them by filling total 3 orbitals. All the electrons will be accommodated. Now none of the electron will go to the anti-bonding molecular orbital, as all of them are accommodated in the bonding molecular orbitals, right? So this will give rise the bond order, what it will be. Now this time it will be 6 electrons in bonding molecular orbitals minus 0 in anti-bonding molecular orbitals divided by 2. It will give rise 3 pair of electrons will be present between 2 oxygen atoms, right, in the form of an ion, that is O2 plus 2. Molecule will hold 3 of the bonds between the two atoms, right. So this is, again look, there is none of the unpaired electron present, all of them are accommodated, so we will say that O2 minus 2 and O2 plus 2 both are diamagnetic in nature, while only O2 is paramagnetic in nature, right. Now here comes the next one, the last one of the structure, molecular orbital theory diagram of F2 molecule. Fluorine comes with the atomic number 9. So here its configuration given 1s2, 2s2 and 2p5. Now you have to accommodate for the 2s orbitals, 2s of one and 2s of the other. They overlap to produce bonding and anti-bonding molecular orbitals, which are sigma 2s and sigma star 2s, each hold 2 electrons in each, so the bond order comes out 0 for 2s. Now we have to find out the bond order for the for the p orbital. The 3 p orbitals of each atom, they arrange themselves in such a way. The energy diagram is similar to that of oxygen. Here you can see sigma 2px is lower energy as compared to pi 2py and pi 2pz, right. Now here the 5 electrons are present for each of the p orbital, so they are accommodated like this, that one of the p orbital will hold 1 electron while the other two will hold a pair of electrons. In total we have 10 electrons to be accommodated, so place 2 electrons in sigma 2px, then 4 will be accommodated in pi 2pz 2py. Then we have the anti-bonding molecular orbitals higher than that of the bonding molecular orbitals of pi type. So, and we have still 4 electrons to be accommodated as the 2 degenerate orbitals are available. So, each orbital will hold 2 electrons in it. This one will be the pi 2 pi 2py and pi 2pz, each will hold 2 electrons as it is given, and sigma 2px will stay empty. This is how the compound is going to have the fulfilling of the electrons, which are 10 in number, 5 from each side of the fluorine atom. Here, what do you think about whether it will be paramagnetic or diamagnetic? You can see none of the unpaired electrons present in this molecule. All are paired, so no deflection in magnetic fields means it will behave diamagnetically. Right? Now this is what we say is the molecular orbital diagram of fluorine atom. One thing more, write down its bond order. The bond order will come out as 6 minus 2 upon 2. 6 minus 4 upon 2 is equal to how much? 2. Only 1, not 2, it will be 1, right? So only one bond can be formed between two fluorine atoms. Here it is given its electronic configuration, in which the filling order is like this: sigma 1s2 will be filled first, and then sigma star 1s2, sigma 2s2 will be filled next higher, sigma star 2s2 onward, then sigma 2px, sigma 2py1, not sigma, pi 2py1, pi 2pz1, each will be filled with 2 electrons, and then their antibondings, that is pi star 2py and pi star 2pz will be filled at the end. Right? Now this is the configuration for fluorine molecule. You have to learn them well, practice them, and then find out the behavior of the molecules, whether they are paramagnetic or diamagnetic, why there is a difference between the energy diagrams of nitrogen and oxygen or nitrogen and fluorine, why there is such a difference between the two orbitals, why the overlapping occur in case of nitrogen, why not in oxygen or fluorine. Find out the reason for them. Read the lecture in from your book as well, right, along with this video, so you will easily get the diagrams, or you will easily get that how you have to draw the diagrams, and you have to remember the main points of the theory, right? Practice it and then tell me whether you got it or not.